Hello again. So, we discussed the connection between optimization and variational methods and finite variable optimization problem and calculus of variations, and this being an alternative to what we call vectorial methods or force balance for statics and Newton's second law for dynamics, right. But then just as there is this optimization in mechanics, we also have optimization in design or structural optimization. A typical problem looks like this is what we discussed: minimize an objective function with respect to some variables. Objective function is going to be function of variables, optimization variables, as well as some what we call state variables. They are governed by some equations which will be constraints, and there will be constraints on resources and then constraints on performance. There will be limits on the variables. All of these make up an optimization problem where there is conflict between the objective function and constraints, or different terms within the objective function and so forth. Okay. Now, let us look at different types of optimization problems. There are many types of problems in optimization that one can pose. The difference among all these types comes based on objective function, based on constraints, based on variables, and the nature of the problem itself, whether it is global or local. Okay. A number of problems. We will examine all of these one at a time. Okay. But we also need to focus on the difference between calculus of variations and optimization in finite number of variables. That is our objective today, to understand how calculus of variations is different from finite variable optimization. Both are optimizations, but there is a difference. That is what we want to understand. In that process, we also want to look at different types of optimization problems. You can classify based on the objective function. Okay. Objective function, if there is only one single objective, that is very straightforward. You have only one objective, one goal, you can achieve it. But it is not always the case. We have multiple objectives. Just like in life, we have many objectives. We want to do that, we want to do this, and we want to do several things at the same time. There we want to define the notion of an optimum. Okay. Further, there is a concept called Pareto optimum. Those of you who would study multi-objective optimization will definitely have to understand what this Pareto optimization or Pareto optimum is. Okay. Overall, in this course, we will be sticking to only single objective, that is only one objective. We will not deal with multiple objectives, but just know that there is a single objective optimization, there is also multi-objective optimization. Okay. The other is whether your optimum is global or local. Okay. What does it mean? Are you first in your school or you are first in the entire country? Okay. If you are first in the entire country or even entire world, then you are a global maximum. If you are only first in your class, then you are a local maximum, right. That is what we mean by global and local. We will be discussing more of it in later parts of the course. Okay. Local optimum is an optimum only in the vicinity, in your neighborhood you are the hero, you are the best. Okay. Global optimum means that you are the best among all the people who existed, let us say all the time, right, then you will be a global optimum, right. So, you have to understand the difference between global and local optimum. Okay. That is, there are global optimization problems, there are local optimization problems. There are single objective optimization problems, there are multiple objective optimization problems. That is one type of classification. You can also classify based on constraints. You can have optimization problems without any constraints, in which case we call it unconstrained optimization. There are no constraints. Okay. When you have constraints, it is constrained optimization. That is a classification based on constraints. Whether you have constraints or not, you get two different types of problems. When you have constraints, constraints can be equalities. Okay. There is an expression equal to something, usually we write it as 0, that will be equality constraint problem. You can also have inequality constraints, less than or equal to 0, greater than or equal to 0 of an expression. Okay. So, constraints can be equality constraint, inequality constraint. And when you have constraints, we talk about what is called a feasible space, meaning the space, you have a search space. Whenever you are optimizing, your variables will be defining a search space. If there are two variables x1 and x2, your search space will be a plane, a 2D plane, okay, or a surface like a spherical surface or a conical surface, where you have two variables x1 and x2. Okay. But then when you have constraints, part of that space will not be permissible, will not be available to you. Then we define this concept of feasible space, that is, every point in the feasible space is going to satisfy your constraints, be them equalities or inequalities. Okay. Whether they are equal inequalities, all the constraints satisfied by all the points in a space which we call feasible space. Okay. So, first you have to construct a feasible space and search in it to find the best. That is what we need to do in constraint optimization. You can classify them based on the nature of the objective function and constraints. For example, if you have constraints, let us say objective function and constraints, all of them are linear, we call it linear programming problem. In operations research, most of the problems are linear. That means that objective function depends on the design variables in a linear fashion. Okay, you only have x1, x1, x2, x2, x1, x2, x3 as linear variables, and you do not have terms like x1 square or x1 times x2 will not be there. Okay. That is a linear programming. There is something called quadratic programming, where your objective function is quadratic. That means that it will have terms like x1 square, x2 square or x1 x2, things like that, they are all quadratic. Okay. But constraints are still linear in a quadratic programming problem. The word programming itself is not computer programming, although optimization problems are solved using computers, that is not computer programming. Here it is just that optimization process is called programming. It is a historical word that just was coined and got stuck. It all happened before the actual programming, computer programming started. Okay. Linear programming has nothing to do with IT in a way. Okay. It is you still need to do using computer to solve these problems, but that programming is different from coding that we do in computer science. Okay. There is nonlinear programming, where objective function and constraints are nonlinear in terms of variables. And then something called geometric programming, where the objective and constraints are, this is not a spelling mistake, it is not a polynomial, it is a polynomial. Polynomial is a polynomial with positive coefficients. If you have ax square plus bx plus c, where a, b, c are all positive, such a polynomial is called polynomial. If all of them are polynomials, that is positive polynomials, then such a thing is called geometric programming. It has some special properties that one can exploit to solve such problems. There is something called convex optimization, where your objective function constraints are all convex. Okay. Then you have convex optimization. There is also non-smooth optimization, where objective function or constraints are not differentiable, meaning that they do not have a well derivative or gradient at all points. Such problems are called non-smooth optimization problems. There are many more categories that one can have for optimization problems based on the nature of the objective function and the constraints that are there in the problem. This thing about global and local, we discussed it earlier, but here we are showing in the pictorial fashion. If I have a function, this blue curve coming down, going up, reaching a maximum, reaching a minimum, another maximum, another minimum, another maximum, another minimum, all these minimum points are what we call minima as a plural. They are all local minima, only in the vicinity they are minima. If I look only in this region, that is a minimum. If I look only in this region, that is a minimum. If I look only in this region, that is a minimum. If I look at the entire region here, then these are not the best minima. The best one is here, that is a global minima. Global minimum is also a local minimum. Just like if you are the first in the country, you are also first in your class, right. It is also a local minimum, it is a global minimum. It is the least among the local minima, we call global minima. So, you can optimize globally or locally. Okay. And the variables that you have can be deterministic or stochastic, that is another classification. Okay. So, your variables are all deterministic, meaning that they have definitive values, you have deterministic optimization. Most of the engineering problems will have deterministic optimization. Okay. But if you look at practically, because any dimension that you take, any material property you take, they are not going to be precisely some value. There is a little bit of uncertainty, then you can do stochastic variable optimization. So, that is another classification, you have deterministic or stochastic. And the variables themselves can be binary, for example, they can take values only 0 or 1, then you have binary optimization, or you can have the variables take only integer values, right, then you have integer optimization, or they will take discrete set of values, but not necessarily integers. If you have such a thing, you will have discrete optimization, right. If you are doing, let us say, mechanical design, you cannot have bearings of any diameter that you want. What is available in the market will be a few diameters, or a screws, length of a fastener, or gears, whatever you take, there will be a certain variables values, then that is a discrete optimization. Okay. So, variables themselves can be, as we already said, deterministic or stochastic. Okay. All these are finite variables, meaning you have x1, x2, x3 up to xn. Okay. These variables are finite in number. Okay. There is, in this case, n that we have shown. Okay. This is called finite variable optimization, and all these other classifications, local, global, constrained, unconstrained, discrete, binary, integer, quadratic programming, linear programming, stochastic, deterministic, all those are various types of optimization problems. But now what we want to focus on this calculus of variations, how is it different from the rest. Okay. For that, let us take this fun problem, if I may say. There is a swimming pool, in the water there is a rubber duck that a kid has thrown in, and the child's dog is here, which is asked to fetch that rubber duck. Okay. So, and the child is impatient, he wants this rubber duck as quickly as possible. So, the dog has to reach this rubber duck in least time. Okay. Least time meaning the lowest time or the quickest, right. There is a sense of optimization. Which path should this dog take in order to reach the rubber duck? Will it go along the straight line, that is the solid black line, which is the minimum distance path from where the dog is to where the rubber duck is, or should it take a different path? Why would it take a different path? Why not the least distance path? Because dog can run on the swimming pool floor at some speed, and it can swim in the water at some other speed which is lower than what it can do by running on the swimming pool floor, right. So, if it takes like this, it will be taking a long distance in water. So, instead dog comes here and then goes this way, it can be shorter, right. So, for example, this dashed line 1, this path looks shorter in water compared to this line segment from here to here. I do not think dog would do this unless dog is sure that it can run fast, swim in water faster than running on the floor. Okay. But there are a lot of possibilities, right. So, such a problem is different from finite variable optimization problem. Here we do not have x1, x2, x3, x4 and xn. Okay. We want to find a particular path. If the dog takes that path, it will reach the rubber duck in the quickest time, in the least time. Okay. The variable in such a problem is a continuous function that represents this curve. Okay. That is the essential difference between finite variable optimization and calculus of variations. Okay. If I put it mathematically, like I said like in the last lecture that optimization is mathematical, everything is analytical, right. We call it analytical mechanics or analytical dynamics. Optimization is very analytical, we can pose problems mathematically. Okay. For this, if I denote speed of the dog as Vx, okay, that is as a function of x at different values of x it has different speeds. There is some speed in the flow, some swimming speed in water, that Vx is given. Let us say that Vx is ds by dt, the speed, right. So, s is the variable that goes along the curve, okay, this way or that way, ds by dt. That ds can be written as, using Pythagoras theorem, square root of dx square plus df square, that is f is a function that I am taking. If I take any little thing, there will be vertical df and then dx, the ds is that. Okay. So, square root, you take this speed and try to find the time dt to traverse a small ds. Okay. We have the ds that we have here divided by the speed that we have, then that equation basically gives us dt. So, I have taken dt that way and try to get this, I have the distance that I have divided by that speed gives me time. Okay. This is the distance ds divided by the speed gives me the time dt. I want the total time for the dog to go from here to there, then I integrate. That is how we get these integrals in calculus of variations. Now, I am integrating this dt from 0 to capital time t, capital T, the time t, that is equal to integral of this quantity, and I have done little thing here. I have divided the two terms by dx square. Okay, that means this is going to become 1 and this is going to become df by dx square, and then the square root of dx square, which is the thing that we have there, multiplying dividing, if I say, that has come out here, the dx. Basically, I have taken dx out of this and v of x is still here, I got an integral. Okay. So, now what do I need to do? I want to minimize this time of going from where the dog is, where the rubber duck is. So, I have 0 to L square root of 1 plus df by dx square by Vx dx. And what is my variable? The function itself, what we showed in the previous slide, right. There are many possibilities of paths from where the dog is to where the rubber duck is, and that function is my variable, and that is the nature of calculus variations. Okay. It may look at the first sight formidable, but then a dog apparently does that. People have done these fun experiments, going to the beach and throwing a frisbee into ocean, and the dog was observed to take the quickest path rather than the least distance path, which is the straight line. Okay. So, dog knows how to solve calculus of variation problems such as this. Okay. That means there is sense of purpose for the dog and there is sense of purpose here, and that is what we are going to discuss. How do you solve the problems like that, a problem that a dog can solve? Okay. One way is to convert that into discretized problem, that is, we want to know where the dog should be for different values of x as it starts from here and goes to the duck, which is at the origin, let us say. So, I want to know what is this point, it is here, what is that point, I am discretizing along the x axis. So, I want to know not the continuous function, but I want to know what it is here, 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 what is that function, what path should I take. When I take that, then this f1, f2, f3, all these heights of this become my variables, then that becomes finite variable optimization problem, as opposed to calculus of variation problem where the function itself is an unknown. Okay. That difference has to be understood very clearly at the outset of this course. Calculus of variations has unknown variables or optimization variables as functions and not as discrete variables. So, here if we take calculus variation problem, we have an integral minimize t, which is defined in this particular manner. It depends on the derivative of this function f, and v of x is given to us. We are optimizing this or minimizing this with respect to the function itself, as opposed to discretized problem we are minimizing with respect to a finite number of variables f1, f2, fn, and you have an objective function which is a function of all of those, just like here it is a function of the objective function. The objective function here is a function of f of x, here objective function t is a function of these finite set of variables. This is normal optimization, what we call finite variable optimization. This is calculus of variations. Okay. So, let us look at the similarity and differences. In finite variable optimization, you have variables that are finite in number, that is a few of them 1, 2 up to n. Each variable may be continuous, it can be a real number or a complex number, a discrete set of values like binary, integers or whatever. Here unknown is a function. Okay. There can be many such functions that are unknown, just like we have finite variables many, here also you can have many functions if you want. Okay. And in this case objective function constraints are functions of these finite variables. Here they are functions of these functions. Okay. Objective function and constraints are functions of functions which we call a functional. Okay. But calling them functions of functions will be actually incorrect, as we will learn later. But know that not only it depends on the unknown function, but like in our previous example in the duck problem, it can also depend on the derivative of the problem. Here it does not depend on f of x, it depends on df by dx. Okay. So, objective function constraints here can be functions of the function and its derivatives. Okay. The notion of a functional which is what we call this integral, we will deal with it later, but understand that it can depend on the unknown function and its derivatives. Okay. And again I want to emphasize that calculus of variations is analytical, it is not a computational technique, it is an analytical technique where you are going to write everything in terms of symbols. Okay. Because the function is unknown, if the function is unknown you are going to have a lot of symbols. Okay. In order to solve it using computer, we have to establish some conditions for optimality, necessary conditions, sufficient conditions, and that is how we will move on. Okay. Calculus of variations, when you establish the conditions of optimality, it will lead to differential equations, whereas if you do an optimization problem in terms of finite number of variables, you will get algebraic equations. Okay. Whereas when you deal with calculus of variations, you are going to get differential equations as the necessary conditions, and it will lead to boundary value problems and initial value problems with boundary conditions and initial conditions. Okay. And if you want to compute a solution, then you have to solve those equations. Okay. In the computer when you do it, you might discretize, that is a different matter, but what calculus of variations gives you is a set of differential equations. They can be ordinary differential equations, they can be partial differential equations. Many problems in geometry, mechanics, physics, chemistry, economics, in all branches of science and engineering and even humanities, you can deal with optimization problems and calculus of variations problems also. And for structural design or design in general, calculus of variations is very important. Okay, as we will see in this course. Okay. Let us look at these variational methods in mechanics first. Okay. So, if you have a beam like this which is fixed on this side as well as on this side, there is some loading on it. It is going to deform and take a deformed shape. Okay. The beam has the freedom to deform to any shape, but it does deform to a particular shape because that particular shape minimizes the potential energy. Just like we saw a spring with a mass, it displaces by a quantity which minimizes the potential energy. Similarly, this beam will deform to a particular shape which minimizes the potential energy. So, it is a calculus of variations problem because the deformation of the beam, if we call it Wx, that is an unknown function. Whenever a function is unknown, it is a calculus of variations problem. In the case of structural design, let us take the same beam fixed on both sides. Cross section area profile can be different from point to point. This is not how we see normally beams in any room, there will be uniform cross section. Okay. But one can make variable cross section beams, and that is a structural design problem. There what is an unknown? The area of cross section A of x. If I say this is the x axis from 0 to some value L, A of x is an unknown function. That is my calculus of variation problem again, because it is not the finite set of variables that are optimization variables, but the function itself is an unknown. That is a calculus of variations problem. Okay. So, we saw both in mechanics and design there is calculus of variations and there is optimization in general, and this is an alternative to our classical way of looking, vectorial way of doing mechanics and that way of doing design. In this course we are going to use calculus of variations, that is why we are going to spend a lot of time on understanding calculus of variations. Now, let us see where it lies in the panorama of optimization problems. We have unconstrained and constrained problems with equalities and inequalities or both, and there is linear programming, there is nonlinear programming, there is quadratic programming, convex programming, geometric programming, dynamic programming, all of those are semi-different programming. It can be non-smooth or smooth, that is differentiable here, all the things are differentiable here, they may not be differentiable, meaning they do not have a unique gradient or derivative, and there can be single objective or multiple objectives, and you can have functions of as variables, then you get calculus of variations as opposed to finite variables which are continuous or discrete with the discrete binary integer or discrete real variable set, as opposed to that now you have function variables, then you get calculus of variations. That is what we will discuss later. Again it will be global or local optimization, deterministic or stochastic, and many other types of problems are there. Okay. Thank you.